Okay, so I will take the attendance now. So in the last class, I started discussion of data encryption standard. Right. So a quick review of that, and then we will proceed for today's discussion. So in last class, I also explained transposition cipher cryptanalysis. So we discussed another approach that is a better approach than the brute force. And then we had seen the pattern attack. And then we had seen that the traditional ciphers are block and stream ciphers. And how to approximate one-time paired cipher. That was also another topic which I discussed. And then I discussed data encryption standard. So what is a data encryption standard? Can anyone say? What is data encryption standard? What is this DES? Am I audible? Yes. So what is this DES? It is a cipher, encryption and decryption algorithm, right? Encryption algorithm, yes. And it is 64-bit and it is block cipher, right? What is block cipher? What do you mean by that? Block cipher? What do you mean by block cipher? Encrypt more than one character at a time, or encrypt in a block instead of stream, fixed block. Yes, correct. It is, we have to take a block of certain size and then we have to encrypt the entire block. So the whole plain text is divided into number of blocks and each block is encrypted with this algorithm. That is block cipher. Okay, and in this DES, what is the size of block? What is the size of block? 64-bit. Yes, it is given on the slide. Okay, so it encrypts 64 bits at a time. Right, so block size is 64, it means it can encrypt 64-bit. How it is performed? So there are 16 rounds. Okay, now this is the basic diagram of DES structure. So you can see that the input is 64-bit plain text. So block is plain text is divided into 64 block, and each block is given as an input. Now this input is given to initial permutation. So there are two methods which we have seen till now. One is substitution and second is transposition. So this is permutation shift the position of the bits, right? And then we apply 16 rounds. Each round is having one input. That input is key. And this key is of 48 bit. But this 48-bit key is generated from 56-bit cipher. So there are 16 different keys. Each key is for one round, and that is generated from 56-bit cipher key. Okay. So naturally, because this is 64-bit and this is 48-bit, so if we want to perform some operation for a round, we have to make certain modifications. And those modifications we had seen in the subsequent slides. So basically input is 64-bit. So that input 64-bit is divided into two halves. Left part is called as of 32-bit L, and right part is called as R of 32-bit. So there are two 32-bit blocks of one 64-bit block. One is L and second is R. And we had seen the equations which are used in rounds. So this is a one round in DES. One round. This diagram shows one round in DES. And all 16 rounds are like this. Basic structure of the round is same. Right? So round I means 64-bit in ith round, that is Li of 32-bit and Ri of 32-bit. So what is Li? Li is Ri minus 1. So if it is L1, it is R0. Okay, and you can see that Ri minus 1 is given directly to Li. Okay. Second is Ri. So what is Ri? Ri is Li minus 1, that is this. It is XORed with another function f. We call it as a round function. F has two input. One is Ri minus 1 and second is Ki. Okay. So for each round, there is one key and its previous round right half. These two are given as a function to a round, and that output is given as an input to XOR, which is XORed with Li minus 1, and the result is stored in Ri minus 1. So here we have a swapper and here we have a mixer. Okay. So this is the basic structure of a round or a round in a DES. Okay. Then we had seen that the overall DES function. Okay. The slide which I have shared, in that I have written this expansion D box, but it is actually expansion P box. Okay. So I will modify this and upload it again. So expansion P box means permutation. Expansion means what we are giving to XOR. XOR has one input of 48-bit. But what we are giving here, Li minus 1. Li minus 1, what is the size of Li minus 1? 32. But F, what is the output of F? 48-bit. Because here you have 48-bit, right? So this is supposed to be 48-bit. So here, if we give 48-bit, then this will not work, right? Because both are different. So we have to convert, because this one is also of 32-bit, 32-bit and 48-bit. So we have to generate 32-bit XORed with 32-bit so that we can store it in 32-bit. Okay, because RI is 32-bit. So we need here 32-bit. Okay. So what is happening here is that first we have to perform XOR, and that XOR is of this function ki 42-bit, and then we have to expand permutation, expansion p box. So what we are doing here is after XOR, we are giving it to S boxes. What is this S box? S box is substitution box, and substitution box are of number 8. There are total 8 substitution box. S, 4, 8 S. There are 8 substitution box. And then there is a straight P box that is also resulting into 32 bits. So this is the function of DES. Fi minus 1, Ki minus 1, Ki. Fi minus 1, Ki. So this key which we add to XOR, that is called as whitener. Okay. Now we see what this S boxes is. S boxes is expansion P box. We have 32-bit. So that is converted into 48-bit because our key size is 48-bit. So first we will convert this 32-bit into 48-bit, and then we will perform XOR. So that XOR results into 48-bit, and that 48 with the help of S box is again converted into 32-bit. Okay. So substitution box is of 6 cross 4. That means there are 6 input and 4 output. So in one box, we have 4 output. So in 8 boxes, we have 8 into 4, 32 output, right? So we are getting 32-bit input and we are also getting 32-bit output. But before converting 32 into 32, we expand, substitute, expand, XOR, substitute, and permute. So these are the functions which are carried out. Okay. So this was discussed in the previous class, and expansion permutation was also discussed, that that is converted into 32 into 48. So how this expansion P box is generated? This converts 32-bit into 48 bits. For doing that, this first bit is taken what was on the last bit, and last bit is taken what was on the first bit. Okay, and after each block, the last bit is from the previous next block, and first bit is from the previous block. Right. So this way we are expanding 48-bit, and this is the expansion P box. I will modify this P box name. Only name is an issue. It should be called as P box, and this is fixed and it is given. Okay. So this was the last topic I covered, and we continue from that point. So this is what I discussed. This is the function F. This is S box and expansion P box, expansion P box table. What is that expansion P box table? That means what is stored on 32nd bit in plain text, that is given as the first bit in this. So it is a permutation. So what is first bit? That is stored on second bit. What is second? That is on third. What is fifth? That is on eighth. 3 plus 3, 6, right? 6 column, 8 row. So 48 bits. Okay, 48 bits. So this is fixed, and that is given here. Okay, now this was the first step. This was the first step, expansion. Okay, expansion was the first step. Now what is the second step? Second step is XOR. I think I'm getting some noise over here. Is the clear? All of you can hear me without noise? Or some? Can you hear me? Yes, can you hear me? Now, when the noise is gone, now clear? Now clear? Is that clear now? Am I audible now? Perfect. Okay, perfect. Very good. Okay, so second step is XOR, and that XOR step is straightforward. That is A XOR B. So 0, 0. This I think you have already studied in your DDC course. So 0 XOR 0, that is 0. 0 XOR 1 is 1. 1 XOR 0 is 1. And 1 XOR 1 is 0. Okay. So this is the second step which is followed. Third step is S box. You can see third step is S box. Okay, this is first step, this is second step, this is third step. So what is that third step? S box. S box is of dimension 6 cross 4. Each S box is of dimension 6 cross 4, which means it maps or substitutes 4 bits for 6 bits of input. So there are 6 bits of input and it maps it to 4 bit. So how it is done? So 6 bits of input, that means 2 raised to 6, 2 raised to 6, that is 64 values. And these 64 values are arranged in 4 rows and 16 columns. You can see that this is first row numbered 0 and there are 16 columns numbered from 0 to 15. Okay. So there are 4 rows, 16 columns, and this results into 64 values, and that is shown over here. So each cell has a value from 0 to 15, and each output entry, this value is of 4 bits. So we use 2 bits to number rows, and in each cell of the row, okay, row and column, each cell of the row column, we have 4-bit value. Okay, 4-bit value. We will see different S boxes now. So DES uses 8 S boxes and each with 6-bit input and a 4-bit output. So what is the input? 6-bit. What is the output? Each cell is of 4-bit. Okay, each cell of the S box is 4-bit. So the output is 4-bit. The 48-bit data from the second operation is divided into 6-bit chunks, and each chunk is fed to a box that you can see over here. This is the output is 48-bit of this XOR. So 48-bit is divided into 8 groups. Each group contains 6 bits, and these 6 bits are given as an input to S box, which produces each S box gives output of 4-bit, and 8 such 4-bit output results into 32-bit group. Okay, so that is shown over here. So the substitution in each box follows a predetermined rule based on 4 rows by 16 column table. So the combination of first and sixth bits, say first and sixth of the input defines one of the 4 row. You can see that input is 6 bit. So bit 1 and bit 6 defines one of the 4 row. There are 2 bits 0, 0, 0, 1, 1, 0, 0, 1, 1. So there are 4 values 0, 0, 0, 1, 1, 0, 1, 1, 0, 1, 2 and 3. Is that clear? Is that clear to all of you? Yes, are you there? Okay. We have 6 bits, that you understand, Urjit? Okay. Now, if we have 6 bits, let us take this 6 bits 1, 2, 3, 4, 5, and 6. There are 6 bits. Can you see that 6 bit? Right? So now we have bit 1 and bit 6. Can you observe bit 1 and bit 6? Right? So we can generalize it like this: x1, x2, x3, x4, x5, x6. Okay, let us generalize this. So x1 is the first bit and x6 is the sixth bit. So a combination of first and sixth bit, x1, x6, that defines row, and combination of x2 to x5 defines one of the 16 columns. Is that clear now? Yes, Urjit, is that clear now? Okay, we will have an example. It will be followed by this slide. Okay, so each S box has its own table. So these S boxes that you are seeing over here, S1, S2, S6, X8, each box has its own table. That table we will see. Sorry. So you can see this table, S box 1. Okay, so it is having how many entries? S box 1 has how many entries? Six into 4, 64, or 4 into 6, 64. 4 into 6 into 4, no, not 6 into 4. 4 into 6 is also not correct. 4 into 16. Yes, 4 rows, 16 columns. Okay, 4 rows, 16 columns. So 64. Total values are 64. How many entries are there in S box 2? 64. Yes. So each S box is having 64 entries, and each S box is a unique, and that is fixed. Okay. So first S box, you can see it is given over here. Okay. So these are the values. So 14, it means that we have 64 bit, and those 64 bit has one of the bit is 14, number 14. Okay, that bit is put as first bit. Okay, so this is the value. So 14 is a 2-digit number. Can you represent 14 with 4-digit binary? right? So, and if you look at these values are from 0 to 15. So see, 14, 4, 13, 1, 2, 15, 11, 8, 3, 10, 6, 12, 5, 9, 0, 7. All these values are coming in the range of 0 to 15. Here also in second row, third row, okay, fourth row. So values are all values are from 0 to 15, right? So that is what I have shown here. Value from 0 to 15, and each output entry is of 4 bits. Because it is from 0 to 15, it can be represented by 4-bit binary number. Is that clear now? Okay. So there are 8 such S boxes. I have not filled this table. They are given in the textbook. And when I will circulate the slide, I will fill this table. But you should look at the textbook chapter number 6. Okay, this is 7 and this is 8. Okay, there are 8 such S boxes. Now we see example. Okay. So first example, the input to S box 1 is given as 6-bit binary. What is the output? Okay, 6-bit binary 1 0 0 0 1 1. Okay, it means that this S box 1 has an input 1 0 0 0 1 1. So what is the output? We want to know the output. Okay, so how to see that? Now Urjit and others, those who could not clear your concept of x1 to x6, now you can see. If we write first and sixth bit together, that means first bit is 1, sixth bit is 1. Is that clear? Right, so first and sixth bit writing together results into 1 1 in binary. Okay, so what is the 1 1 equivalent of binary in decimal? 3, right? So 1 1 in binary is 3, and that represents row number. Okay, can you see 3 here in row? Can you see row? Yes, okay. Okay. Now the remaining bits, these underlined bits are bit number 2 to bit number 5. Okay, so 0 0 0 1. Okay, so this is in binary, 0 0 0 1 in binary. So what is the equivalent of this in decimal? 8421. Remember 8421? Do you remember 8421? Last bit is 1, so it is 1, right? So that is 1. Okay, so that is the column number. Okay, so row number 3, column number 1. What is the value at row number 3, column number 1? 12, right? Now, can you represent 12 with 4 bit? So how you can represent 8421? 1100. Yes. Yes. So the output is 4 bit. Output is 4 bit. Understood? Input is 6 bit. Output is 4 bit. Got it? Okay. So 3 1 is equal to 12, which is 1100 in binary. And so the output is 1100. That is 4 bit. So input is 6 bit, output is 4 bit. Is that clear? Understood, Urjit and others? Okay. Now do this second example. The input to S box 8 is 0000000, 6 bits. What is the output? Okay. So how to solve this? First bit and sixth bit together taken. So that is 00. Okay. And 00 in binary results in 0 in decimal. So that is indicating row 0, in which S box? S box 8 is 0, right? So here we have this S box 8. Can you see this? Okay. And in that 00, right? 00, that is row 0. Okay. Now, remaining bits that are underlined bits are all zeros in binary. Again, it is 0. So row 0, column 0. In which S box? S box 8. So you can see S box 8 has row 0, column 0. What is the value? Now, what is the binary equivalent of 13? So that is the output. Clear? Okay. Now, so what we have done, what is the input to S box? All S box, how many bits are input to S box? Total, all 8 boxes have input of total how many bits? 48 bit. And what is the output? 32 bit. Okay. So that is step 3. Now we have in step 4 that 32 bit is the output of step 3. And that is permuted. Okay. That is permuted. So again, it will create the 32 bit output, but that is after permutation. So that permutation is done by P box. Okay. So function creates 32 bit and the output 32 bit from F are XORed with L to create the right half of the output. So Li equal to Ri minus 1 and Ri is equals to Li minus 1 XOR F Ri minus 1 Ki. We have seen this F function. Now it will be, so the output is 32 bit. This 32 bit is XORed with the output of F and that is stored in Ri. Is that clear? Is that clear to all of you? It is not an example, it is a process. You don't need example. You have to first understand the process. I'm talking about the process. You understand the process, what we are doing, right? So this is only F function. It is only F function. And there are different stages, step 1, step 2, step 3, step 4. So this is step 4. P box example we will see, but first you understand what is P box. Have you understood what is P box? Straight P box. Have you understood P box? Right? So that P box is permutation box. Okay? Permutation box. So what we are doing is this So this is the initial and final permutation. Okay. So in this Li and Ri, if you recollect what we used to do in fact, it is also given in the beginning. See, can you see? Initial permutation, round, there are 16 such round, and then final permutation. What is there in round? There are two left bit and right bit blocks, 32 bits blocks, and then this round is performed. And we have seen this round function we have seen, and in that round we have f function. So we have just now seen this f function that is XORed with Li, and this result is stored in Ri. So this is the formula. Can you see this? Is this process is clear, right? Now after this process we have permutation. Okay, so that we will see now. So this process of round is repeated 16 times so that the resultant ciphertext can't be cryptanalyzed easily. The objective of permutation was that if we do the permutation, any attacker will find it very difficult to perform cryptanalysis, because it was assumed at that time, and it was true also, that in those days computers were slow. Today you have very fast computer. Even your desktop computer is so fast that in those days when the DES was found, it was in around 1976. Today's desktop computer used to be high performance computers in those days, and they were made up using technology like parallel computers. And those days the computer capability was very less. So if we do the permutation in those days, it becomes very difficult to perform cryptanalysis. That was the goal, and it was true in those days. But in modern day, with the computing facility has become very fast, this has become little bit irrelevant, right? So we will see that. So in the round structure, we see initial permutation and final permutation. You can see here, I have shown you here in the beginning, there is initial permutation and there is a final permutation. So this 64-bit plain text is first permuted into 64-bit initial permutation that is given to round function. 16 such round are followed with 48-bit key, and then again final permutation is carried out. So it appears to be very complex task, so it cannot be easily decrypted. That is the, so if you don't know all these 16 keys and all these things, then it is very difficult. That is the goal it was set at that time. But there is a relationship between this initial permutation and final permutation. What is that? The initial permutation is inverse of final permutation. Remember that we just don't want to do encryption. We also want to perform decryption. So if suppose, assuming that we have final permutation, and if we have, assuming that we cryptanalyze analyst has able to find 16 keys. So if we perform reverse process of round 16 to round 1, then if we know final permutation, we can easily find the initial permutation because it is the inverse. Okay, and inverse you already know what is the inverse. Okay, so FP and IP are inverses of each other, and that is why, because of the modern day computing facilities and softwares available, FP and IP have no cryptography significance. It only delays the computation, but it will not be impossible to decrypt because we have done permutation. Okay, so in those days, time consuming task was actually adding value to cryptography, but nowadays this has no cryptography significance. But we have to understand because it is part of DES. So what is this initial permutation and what is the final permutation? So these two blocks are given. So this 1, 2, 3, 4, 5, 6, 7, 8. 8, 1, 2, 3, 4, 5, 6, 7, 8. 8 cross 8 block. That results into 64 bits. And this is the initial permutation. Initial permutation means before initial permutation. You can see what is there before initial permutation. You have 64-bit plain text. So that block of 64-bit is permuted with this block, initial permutation. So what is initial permutation block? First bit is 58. That means in the original plain text 64-bit block, what is stored on 58th bit, that is going to become first bit in the initial permutation. 58 bit is going to be the second bit. 42nd bit is going to be the third bit. Is that understood? Understood this point? Initial permutation. Okay, so this is called as initial permutation. Now this initial permutation is inverse of final permutation. So this particular block is actually showing you inverse of this. Okay, I'm repeating though. You can see in this diagram, original DES structure, you have 68-bit plain text input, which is converted into initial permutation. So you have 64-bit 8 cross 8 64-bit block. Okay, so in that you will have 58th bit. So that 58 bit is going to be stored in the first bit position. That is, that way 50th bit is going to be on the second bit. Okay, then 42nd is going to be the third bit. We have already seen this in transposition cipher for 5 bit. So same way, same concept. Permutation, if you can recall transposition cipher, that I already discussed. Okay, so this, all this, so 32nd bit is going to be in 1, 2, 3, 4, 5, 6, 7. 7th row, 4th column. Okay, 7 into 8. That is 7th row. So 6th row into 8. So 48, 49, 50, 51, 52. 52nd bit is what was in the original plain text box 37, that is stored on 52nd. Okay, so this 37 is on 52nd position. Okay, 53, 54, 55, 56, 57, 58, 59, 60, 1, 2, 3, and 4. 64th bit is what was the originally 7th bit. Okay, this is initial permutation. Now this initial permutation and final permutation are inverses. And how do we find that? So if you see, let us see the example. Okay, with this example, it will be clear that final permutation and initial permutation are actually inverses of each other. So if you see that the example says that find the output of final permutation box when the input is given in hexadecimal as 0x this value. Okay. How many digits are there in this input in hexadecimal? Count it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16. So 16-bit hex, that is equivalent to 64-bit binary. 16 into 4, each digit is of 4-bit. Is that clear? Right. So I have shown you here that this hex value is represented in binary of 64-bit. You can see. And 1, 2, 3, 4, 5, 6. First 6 bits are 0. So you can see first 4 bit, second, third, fourth, fifth, and sixth. 6 4 bits, 6 into 4, 24. Right. Now, seventh 4th bit is having value 8. What is the equivalent of 8 in binary? Equivalent of 8 in binary? 1000, right? So that is 7th 4 bit. So this is 7th 4 bit 1000. Okay. So that means which bit is having 1? What is the number? 1, 2, 3, 4, 5, 6. 6 into 4, 24. So 1 is on 25th position. Understood? 1 is on 25th position. Clear? Can you see this mouse pointer? It is pointing to 1, which is 25th position. Okay. Now, another value, all other values are 0. Last 4 bit are having value 2. What is the binary equivalent of value 2? 4-bit representation. Represent 2 in 4-bit representation in binary. 0010. Yes. So that is exactly what you can see here. The last 4 bits are 0010. So this 1 is on which position? What is the position? So total 64 bits. First 15 blocks of 4 bits, that is 60, then 61, 62, 63. Okay, 63. This is the position. Clear? Right? So 25th bit and 63rd bit, these 2 bits are only ones, other bits are 0 in this hex value. Okay. And so final permutation bit 25. So here you can see what is 25th bit. 1, 2, 80, 60, 24. 25th bit is 64. So 64th bit is having value 25. Okay, 64th bit is having value 25. You can see bit 25 and 63 are ones. So in the final permutation, bit 25 becomes bit 64 and bit 63 becomes bit 15. So in initial permutation, what is 63rd bit? This is 1, 2, 3, 4 up to 8. 8 into 7, 56, 57, 58, 59, 60, 61, 62, and this is 63rd bit. Okay, so 63rd bit is having value 15. So here this 15 is going to be on, so 15th bit is going to be 1. So 8, 9, 10, 11, 12, 13, 14 and 15. Okay, 15th bit is 63. Okay, so here 15 is here, 15th bit is 63. So what is stored on 63rd bit is 15. That 15th bit is stored 63rd. Is that clear? Twenty-fifth bit is having 64. So 64th bit is having 25. Clear? Right? So the result is 0002. Okay, 2, because why 2? 25th bit 8421. So 000 24. Okay, then 15, right? So 8421. So we take this value. Okay, this is 2. 25th becomes 64. You can see 25th bit is 64. So 64th bit becomes 25 and 63rd bit is 15. So 15th bit is 63rd. Okay. Now this value is converted into hex. So the last bit, 64th bit is 1 and 15th bit, okay, 8421. So 0020, right? So 8 plus 8, 16. 25th. Okay, so I will cross check this value. I think it is correct. 0084, 8, no, sorry, I have made the wrong calculation. 1, 2, 3 is multiplied by 4. So 4 plus 4, 8 plus 4, 12, then 13, 14 and 15. 15th bit is 1. So 15th bit is 8421 is 2. That is why it is 1. Okay, is that clear? It is 2. Is that clear? Understood this 2 value? 1, 2, 3, 4, 1, 2, 3, 4, 8, 12, 13, 14, 15th bit. 15th bit is supposed to 1. 15th bit is 8421, it is 2. So 2 is put here. Is that clear? Okay, let us see second example. Prove that the initial and the final permutations are the inverse of each other, but the finding the output of the initial permutation if the input is this. So this is the final permutation and we have to find initial permutation. So this value, hex value, is written in the binary like this. So this is 16 into 4. Each value is represented by 4-bit binary. So this one is, you can see, 4 plus 4, 8, 9, 10, 11. So here one 4-bit block is missing. So that I will substitute. And then, so 13, 14 and 15. And this one is last one. Okay. So now what we have to do is, the input has only two ones, the output must also have two ones. So using the table, we can find that output related to these are of 2 bits. So here, this bit is 15th bit and that is 1. Okay. So here we have to find 15th bit. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. So that is having value 63 and 64 is having value 25. So what we have to do? 63rd bit and 25th bit should be 1. Okay. So that is 63rd bit is 00. So 0010. So that is 2 and 25th. So 1, 2, 3, 4, 5, 6. 6 into 4, 24. Then 1, 0, 0, 0. That is 8. So this one is 8. And this is initial permutation value. Is that clear now? Hex value. How we obtain hex value? Hex to binary, binary to hex. Clear, all of you? Initial and final permutations are inverses of each other. Okay, so you can see here that, let us take this value 16. Okay, or first value is 58. Okay, so in the final permutation, what is 58th value? 1, 2, 3, 4, 5, 6, 7, 8. 8 into 7, 56. 57 and 58. So 58 is indicating what? 1. So what is stored on 58th position? That is stored on 1. So in final permutation, what is on 58? That should be put into the first position. Is that clear? So position of 58 is 1. So that is on 58 position, it is 1. Is that clear now? Inverse. Okay. So I think I stop here for initial and final permutation example, and then I will discuss the remaining part of decryption, how the decryption is performed. That I will discuss in the next class. I hope that you will study it, because it will not be that easy. So refer to the slides and also read textbook for better clarity. However, this textbook has all these concepts are not straightforwardly given. So up to some point it is straightforward given, but then for remaining part, which I will discuss next, you also have to take help of chapter number 5. So I will take the concept of chapter number 5 to explain you the following topic, right? The next, which will be discussed in the next class. Okay. So you will find it very interesting. I'll stop here now.